All right, today's topic, we're starting our new unit. This is the second unit. We're going to be looking mostly at exponential functions and logarithms in this unit. We're starting off with a look at arithmetic and geometric sequences. So the important thing on this one is that you need to be able to create an arithmetic sequence or a geometric sequence and then use this to solve problems. Let's have a look. So arithmetic and geometric sequences. A sequence of a function is a series of whole numbers. It sort of links a whole number to a real number. So this means that only able to substitute in whole numbers. Typically, we don't use 0 in a sequence. Let me make this off. It usually starts at 1, 2, 3 into a sequence. The first term in a sequence is term 1. The second term is term 2, and so on. So if we look at this sequence here, consider the sequence defined by an equals 4n minus 3. What is the first term in the sequence? So the first term in the sequence is a1. This would be 4 times 1 minus 3. That's going to give us 1. What's the seventh term in the sequence? The seventh term in the sequence is going to be 4 times 7 minus 3. So is that 25? Yep. Oh, no. Are we following? So you have some key formula for arithmetic sequences. So an arithmetic sequence is going to have a constant difference. This is the key to defining arithmetic sequence. Let's look at the example given here. We have a constant difference between the numbers all the way up. What is the constant difference that we see here? What is the constant difference? 3. We go up by plus 3 every time. So one of the most useful formulas, this one I've highlighted in yellow, if you take any term in the sequence, such as we'll take the third term in the sequence, and we subtract the previous term, you'll get the constant difference. That's the formula for it. Any term in the sequence, which is an, subtract the previous term, an minus 1, and that will give you the constant difference. Our standard formula for finding the nth term in a sequence is this one. We take the first term plus n minus 1 lots of the constant difference. These arithmetic sequences tend to be linear functions, although they're discrete functions. They're not continuous. They have a series of dots as you plot them. They don't plot as a line. No. There's no formula. There's no formula sheet for this course. That's what makes it college level mostly. Having to memorize the formulas. It gets pretty tricky towards the end. You're going to have to memorize. So the best thing to do is to work with the formulas a lot, and you start to sort of memorize them. But I find that the trickiest ones will be the trigonometric identities, because they can be very similar. They take a little bit of memorization. It's tough. I think it's one of the hardest parts of this course. Okay, so each of the following, determine if it is a arithmetic sequence or not. What do we think to this first one? Is it an arithmetic sequence? Why not, Bassa? It's quadratic. It's not linear. So this one is not. What about the second one? Yes. This is going to be an arithmetic sequence because it looks linear. What is the common difference? Minus 2. So the common difference in this one is going to be minus 2. If you imagine the function, the first term in the sequence is going to be 4. When n equals 1, we're going to get 4. And every time we increase n, we go down by 2. So the common difference is going to be minus 2. This next two problems, what we want to do is we want to use that formula and see what the common difference is. So between the first two values, how much have they gone down by? Sorry, how much have they gone up by? plus 5. What about here? And does this continue? And here again? This means it is arithmetic. This means it's arithmetic, and our constant difference is going to be plus 5. Let's try this one. What's this one changed by? Minus 3. And here? Plus 5. At that point, we can stop. It's not arithmetic. It's not going to be arithmetic at that point because we don't have a constant. As soon as you get one value that doesn't work, it's not a constant difference. Not a constant difference. This is your typical problem to solve. Let's have a go at solving this one. So, we need to find out what the common difference is first. We need to find out what the common difference is. If you imagine the sequence, we've got A1, A2, A3, A4, A5, and A6. To move between these, we add D. We keep adding our D, plus D, plus D, all the way up. We are given this value here. We're told that this value is equal to 8. And we are trying to get, we are told that this value up here is equal to -1. How many lots of D do we need to travel? Do we need to add? 3. We've got plus 3 lots of D here. So we could, I tend to set the equation up like this. I tend to say, in order to get to the 6th term, from the 3rd term, we add 3 lots of D. So this means that -1 is equal to 8 plus 3D. That means -9 is equal to 3D. D is equal to -3. How many lots of D do we have to subtract to get from 3 back down to? If we move backwards through the sequence, if we want to go backwards here, how many D will take us this way? That's -2D, isn't it? To go from 3 back to the first term. What's the first term going to be? What's the first term going to be? 14. How do we calculate that? Well, if we want the if we want the 3rd term and we're at the first term, we need to add 2D to it. So the first term plus 2 lots of our D, which we found to be -3, has to equal 8. So that gives us 8 plus 6 equals the first term, which means the first term is equal to 14. So our formula for any term in the sequence is AN equals 14 minus 3n minus 1. In this question, we're asked to find the 12th term. So A12 is going to be 14 minus 3n minus 1. Oh, sorry, our n is 12. So we need 14 minus 3 times 11. Use your calculator. What's that one going to give us? That's that. Zach, what did you get? -19. Excellent. Okay, have a go at this question for yourselves. 4 minutes for this one. All right, let's have a look at our answer here on this one. So, first up, we've got how many lots of D is there in order to get from A2 to A6? There's 4 lots of D. So 7 plus 4 lots of D will equal 9. So that means 4 lots of D is equal to 2. So D has to equal a half. So if we're adding a half every time and the second term is 7, what was the first term? So the first term is going to be 6.5. So the nth term in the sequence is going to be 6.5 plus a half n minus 1. Don't forget the n minus 1 inside there. Don't forget the n minus 1. We wish to find the 24th term, A24. We need 6.5 plus a half times 23. This gives us 18. Okay, so our next type of sequence is called a geometric sequence. And what's important about a geometric sequence is these ones have what we call a common ratio. And subsequent terms in the sequence have a common ratio. What this means is we're always multiplying. So in the last one, we're always adding the same number. So here we're always adding the same number in the arithmetic ones. In the geometric ones, we're always multiplying by the same number. So if we multiply 8 by something to get to 4, what is that something? Yeah, a half or 0.5. And if we multiply by a half again, what we get to the next term, and a half again to get to the next term. This is what we identify as a geometric sequence. And this formula in green is really important. So in order to identify something as geometric, you take any term in the sequence. Let's take this one here. So the common ratio is going to be, if we take any term and divide it by the previous term. So the previous term to this one is that one. So we need to divide it by the previous term, and we get a half. This is how we find the common ratio. To get to the nth term in the sequence, we take the first term and we multiply it by r to the power of n minus 1. These functions look and behave like exponential functions. They look and behave like exponential functions. Although they're not continuous, they're discrete. You have a series of dots that perform in an exponential way. They look like exponential functions because they have the n in the exponent. So when you see them in a form like this, the variable is in the exponent. So we have to identify whether these ones are geometric or not, and if so. So the first one, is this one going to be geometric? Why not? Yeah, n isn't in the exponent, so this one isn't. What about the second one? Yes, this one is. The common ratio. The common ratio is the bit that we are putting the n on. So wherever your n is, raising it, that's inside there is the common ratio. So the common ratio in this one is going to be 2. We are going to double it every time with this formula. They tend to look like that one. Let's do the test on this one. So take any term in the sequence. I'll take the 2 and I'll divide it by the previous one. If I take the 6 and I divide it by the previous one, and I take the 4 and divide it by the previous one, Is that the same number? No, clearly not, is it? This one's 2 over 3, this one's 3, and this one's 2 over 3. So it's not quite. It's not quite. So if we take these two give us a 2 over 3, and these two give us a 2 over 3, but 6 and 2 don't. So it's not. It should be so R is equal to any term in the sequence divided by the previous term in the sequence. So this is the first term, the second, the third, the fourth, the fifth. So this is the third divided by the second. This one is the fourth divided by the third. This one is the fifth divided by the fourth. And we see that it's this one that's different to the other two. Let's try the test on these ones. So I'll take minus 8 divided by 16. What does that give me? Minus a half. If I take 4 divided by minus 8, minus a half. If I take minus 2 divided by 4, minus a half. And then last one, 1 divided by 2, minus a half. So this one is geometric. Let's try a similar problem. So if we do what I did last time, we look at it in general terms. If the first term in the sequence is G1, G2, G3, G4, G5, G6, and so on. To move between G1 and G2, I times by R. To move between G2 and G3, I times by R. So I times by R every time. You move up and down the sequence by multiplying by R. But if I want to go from G3 to G6, I'm timesing by R, R, R. So if I times by R, times by R, times by R, that's timing by R cubed. So I need an R cubed here. So I can set up the equation that G6 is equal to G3 multiplied by R cubed. So putting our values in, we get 128 is equal to negative 2 multiplied by R cubed. That means R cubed is equal to negative 64. What's the cube root of 64? Is it 4? So that would give us minus 4. If I want to move back to the first term, so G3 would be equal to G1 times by R squared. Just looking over here, I go 1, 2. This is R squared. So putting our values in, G1 times by minus 4 squared is equal to G3, which is negative 2. Which means G1 equals negative 2 over 16, which is negative 1 over 8. So the nth term in the sequence is equal to the first term in the sequence times the common ratio to the power of n minus 1. We'll need a calculator for this one. We have to find G11. So minus 1 over 8 minus 4 to the 11 minus 1. Type that into your calculator, tell me what you get. Type that into your calculator, tell me what you get. Let's finish this bit first. So we should get minus 131,072. Perfect. So 128 divided by minus 2, minus 64. I don't have to go through G. So in each one of these, I'm finding the first term in the sequence. I don't have to go through the first term in the sequence to get to the one that I want. So let me show you another strategy that you can use. So we find that R is equal to minus 4. We know that the sixth term in the sequence is equal to 128. And we wish to get to the 11th term in the sequence. How many lots of R will get me from the 6th to the 11th? So this should be 128 times negative 4 to the 5. And this will bring us to the same point. It's all about knowing how many lots of R or D you need to move up and down the sequence with. The key concept is that arithmetic sequences were adding and geometric were multiplying. Have a go at this one for yourself. We can have 5 minutes for this one. Okay, so what we need to do is how many lots of R do we multiply G2 by to get to G7? We need 5 lots. 5 lots of R. Let's put our numbers in. We get 48 times R to the 5 has to equal 1.5. So this means R to the 5 is equal to 1.5 over 48. Let's use our calculator for that one. 1.5 divided by 48. And then we'll take the cube root. No, the fifth root. So this means we get 0.5. So the first term in the sequence, G1 times by 0.5 gives us the second term in the sequence, which is 48. So G1 is 48 divided by 0.5. So we just have to double 48. That gives us 96. So the nth term in the sequence, so Gn is equal to 96 times 0.5 to the n minus 1. We're asked to find the 11th term. So G11 equals 96 times 0.5 to the 10. What do we get as our answer here? You get 3/32, or 0.09375. Is that right? All right, our last example for today, modeling question. Sorry? Have a go at this last question. 5 minutes for this one. Let's have a look at this one. So a particular type of bacteria divides into 2 new bacteria every 20 minutes. What is our value of R here? Our value of R is going to be 2. Why? We get 2 new ones every 20 minutes. So if we have 200 at the beginning, so we can get to our answer, so the number of the bacteria, so we can go straight to our answer with bacteria will equal, we'll start off with 200 and we will double it every 20 minutes. How many lots of 20 minutes in 4 hours? 12. This will give us our answer. Let me see my calculator. 819,000. 819,200. Taking a more systematic approach to this one is we would have, if we're trying to find it in the sequence, it would be 200 times 2 to the n minus 1. Now, our first term in the sequence is when we're at 0. So at 20 minutes, it's at the second term in the sequence, and so on. All right, let's finish there for today.